This video lecture will cover section 3.5, which has to do with understanding derivatives graphically and numerically. So in the previous video lectures, we discussed limits and average rate of change, and we can put those two ideas together, and that will give us the instantaneous rate of change or the exact rate of change of a function at a point. So we've provided that definition here as a reminder. One thing to note is that this definition is just letting that point be called x equals a, and so the previous definition we had just had an x there, so it doesn't matter what symbol you use there. That's just representing the point of interest on the horizontal axis that you're looking at and where you want to know the rate of change. So the other thing of interest here is this notation on the left hand side. So you see the apostrophe there, that indicates that's shorthand for the rate of change of the function f at the point a. And so this is representing a number, and that number is precisely the rate of change, how quickly the function is increasing or decreasing at that point. So as I mentioned, this section has to do with understanding these derivatives or this instantaneous rate of change graphically. So let's go to the course website, and I want to introduce an applet there that might be helpful. So if you head to the course website and scroll down on the left-hand side to the very bottom, you'll see practice material. Once you click Desmo's applets, you can choose from a few different applets, but we're interested in the second one. So you can turn different curves on and off by clicking on the colored portion on the leftmost side of the column here. So you can turn the red line off and so on and so forth just by clicking. So let's turn off the green line. And just to make this picture a little bit nicer. So at the very first entry, you can enter any function that you're interested in. And so you can see that's the blue curve here, and this is just a random function we chose. But feel free to change that to whatever you're interested in. And then the red line is something we've seen before. This is what we would call the secant line from the interval 2, and here's the value of h here, so you can change that to be whatever you want. So I'll change that to be 2 as well, just so that I have a nice whole numbers to work with. So this line, you can see the line change slightly. This line just represents the secant line corresponding to the average rate of change over this interval 2 to 4. And so you can play with this yourself and change these values to whatever you want, and you can see how the secant line will change. So here we're at about 5 on the right hand point, so this interval would be 2 to 5, and so this would be the corresponding secant line. So if you're having trouble sketching secant lines, this might be a good tool to practice. You can just turn that off and then choose an interval, choose a value of h. H, remember, is the width of our interval. So if we chose h to be 4, this should get us from 2 to 6, and we see that here, and then we should connect that line to give us the corresponding secant line. So this is a good way to practice and really understand these ideas that we've talked about up to this point. With the introduction of the limit, what we're doing is taking the limit of the average rate of change as our width h, what we sometimes call delta x or delta t, approaches 0. So what are we doing? We're letting that width shrink down about some point. So let's say we'll call a our point of interest. And we can actually physically do this just by grabbing this right-hand point and dragging our secant line. And we can see on the left-hand side what's happening to h as we're doing that. So h is getting smaller and smaller and smaller. So we're dynamically illustrating this idea of the limit as h goes to 0. And so what happens and we can keep zooming in too, and that's kind of one of the nice features. We can just get closer and closer and closer and closer. And eventually, one of the fundamental ideas of calculus is this fact. If we zoom in enough and keep letting h get smaller and smaller and smaller, the curve, which at this point, when we were zoomed out, was looking very curved, very nonlinear, starts to lose its curve. So if we zoom in at a point on any curve enough, the curve will start to look linear. this line, the lines are overlapping now, our curve f of x and our secant line y, and you can see our h is extremely small. So our h is 0.0035, and we could just keep going smaller. But we've already seen what starts to happen, and that is that these functions become indiscernible. So this tells us why taking the limit as h goes to 0 will give us the instantaneous rate of change of the function at that point. And it's from this fact that every curve, at a point, if we zoom in enough, looks like a line in that local area. So that's the idea, and that's what the tool of the limit is doing. So this line that the secant line is approaching has a name, and it's called the tangent line. So remember, the slope of the average rate of change is precisely just the slope of that secant line. So this is calculated below in the applet. We call this m, and that's done for us as well. So you can kind of see what happens as we are dragging that to the slope. So the slope's changing a lot at first. Let me just zoom back out. So you can see, and if we go out far enough, that the slope's even positive. So I'm looking at m here on the left-hand column. M is our average rate of change. It's the slope of this red line, our secant line for this function. So h here is quite large. H is 5.87. That's the width of our interval. And again, let's just think about taking the limit. And one way we can think about this is dynamically, and that is to say we actually let h get smaller and smaller and ask what's happening to m. So here m starts to become negative, and it's still changing quite a bit. But as we get closer and closer to the point and start taking h smaller and smaller and smaller, we'll notice that m stops changing, or it changes very little. So m's about negative 0.13. And we can see that it's still changing as we're dragging these points closer and closer and closer, but it's not changing nearly as much as it was originally. So now it's negative 0.11, and so it's kind of pegged at negative 0.11. It's still changing, but ever so slightly. So this is mimicking what we do when we take limits as h goes to 0 in the derivative. So this slope that this is approaching actually has a name, and it's the slope of the tangent line. So the tangent is the name that we'll use, and that was that first line when we first introduced this applet that was present on the screen. And so you can just click G to see what that line looks like at this point. And as we said, our secant line approaches, as h gets smaller and smaller, approaches the tangent line. So this the slope of this tangent line gives us precisely the derivative or instantaneous rate of change. So the 15th entry here, the last row in this column, actually gives you the value of the derivative. And if we compare that to our value for average rate of change, we see that it's very close. And so sure enough, that's precisely what the derivative is giving us, is the instantaneous rate of change at the point. In this case, our point is x equals 2. So you can play around with this yourself and try to convince yourself of why this makes sense. And so again, just to illustrate what we did, we were thinking hopefully about the definition of the derivative, which is the limit of the average rate of change as our width goes to 0. The slope of the corresponding secant line, so this red line, is the average rate of change. So if you're looking at a graph like we are, you can think of the average rate of change over an interval as the slope of that red line. So as we take that limit, this average rate of change will always approach the same slope as the exact rate of change, as long as we get close enough. And so you can see that that happens as you let h get smaller and smaller and smaller. So we can never actually let h be 0 because of that definition where we're dividing by h. But you can see what happens as we take the limit. It will approach this value. So this also suggests a way for us to draw these tangent lines. And probably the easiest way is to take a small interval like 0.1, or kind of as small as you could draw on your paper, and just draw the secant line of those 2 points. So here in this example, I'm just taking 2 to 2.1, and so you can see the secant line in green is pretty close to the actual tangent line. So you can, again, just play around with this, and you can change your point of interest too. So what about the average or the instantaneous rate of change, or the derivative at 5? You can see graphically the corresponding tangent line, and if you were trying to approximate that with a secant line, you could take a small interval, take those 2 points, and you should get a good approximation of that green line. So play around with this, and also come back to this later as you kind of work some problems and have let these ideas sink in a little. So go ahead and read this page, but the discussion we just had is really a much more detailed summary of what is covered on this page. So in the blue, you can see the really short summary of what we discussed. So the slope of the tangent line is precisely the instantaneous rate of change, or derivative, of a function at a point. Okay? So let's look at a problem and see how we would use the ideas. In this problem, we're given the plot of a population of bacteria t minutes after an infection, and it asks us to estimate this term, g prime of 5, and interpret our answer. So when you see this notation, this prime notation, this is referring to the derivative or instantaneous rate of change of whatever the function is, in this case g, and then the 5 is telling us where to look. We need to know at what point or time are we looking at. So in this case, it's 5. So the way to do that, if you have a plot, is to understand our graphical interpretation, which is the slope of the tangent line. So that's what we just discussed. So you'll go to that point, and so if you can draw the tangent line, then you can find its slope, and you'll have the estimate for the derivative. So we say estimate because we won't be able to draw the precise tangent line because we're just doing a sketch. So as we discussed when we were using the applet, probably the easiest way to draw a reliable sketch of the tangent line is to just draw a secant line with a really small interval width about the point of interest. So our point of interest is 5. We've already marked that. And so just choose a point that is nearby such that the distance between the 2 points is very small. So some point to the left or the right. So it will probably just depend on how close you can make those pencil marks. Find the 2 function values, so just look up and indicate those, and then you can just connect those with a line. So you should get something like this when you just connect those 2 points. So this will do a good job approximating our tangent line, and so then we can just choose 2 points on this line and calculate the slope, and that will estimate our instantaneous rate of change, or our derivative, at t equals 5. So we have a lot of new terms floating around, so I would always encourage you to label things, such as this note here, that this is the tangent line of g of t at t equals 5, so that when you go back and read through this, that's just a little reminder. And also, I would even remind you to say these things out loud to yourselves, just so that these ideas will sink in and you get used to this language and this notation as soon as possible. So in this example, we provided you with the exact tangent line, and so you can actually see that our tangent line really does a good job and agrees with that very nicely. From here, we can estimate g prime of 5 by just choosing 2 points. So let's choose, any 2 points are fine, so just choose points that look easy, that are nice whole numbers. So at the rightmost point, we have about 450. Leftmost point, we have 0. And this ranges from 7 to 4 seconds. So you can see that calculation below, and so that gives us 150, and the units fall from this because we can see here the units in the numerator are bacteria, and the units in the denominator are minutes. So bacteria per minute. So this is our rate of change this estimates our instantaneous rate of change at 5 minutes. So a quick sentence to interpret is provided here. So this means precisely that at 5 minutes into the infection, the bacteria is growing at a positive rate. So it's growing by 150 bacteria per minute at this time. So this question just walks us through a little bit of practice for tangent lines. So I would encourage you to pause at this point and try to answer part A and B by yourself, and we'll go through that now. So here are the results for the tangent lines at x equals -2 and x equals 0. So again, just to walk through that process, I would recommend just making 2 ticks that include the point of interest with the smallest interval width that you can comfortably draw, and then find the function values at those points, and then connect the dots, and that will give you a pretty reliable representation of the tangent line. So that's what we did here at x equals -2, and that's the line that you should come up with, something quite close to this. This will always be an estimation, so if you're working on any problems where you're asked to do this online, then that tolerance would be built into the problem. So as long as you're getting close, then you should be okay. But always just draw those tick marks as close together as possible. So at x equals 0, this is what we should have as well. So just 2 tick marks close together as possible, and then find those function values, and you'll see that you should come up with something like this. And so for the last one, I thought we could go through that together. So the last one should be at x equals 1.1. So let's go there to 1.1. It's somewhere right about here, and we'll make another tick mark as kind of as close as we comfortably can, and the function values are below, there and there. And so from there we can just sketch a tangent line. So you should come up with something like this. So the slope of these lines tells us the derivative, or the instantaneous rate of change, at these points. So part B asks us to estimate f prime of 0. So that tells us that all we need to do is find the slope of that line corresponding to x equals 0. So the tangent line at x equals 0, that slope will give us f prime of 0. So one thing you may need to do when you're using your tangent lines is you may need to extend them if you're looking for points. And so I'm just going to extend this up. You can always extend your lines as needed, and so this gives me 2 really nice points, the point -1, 0, and then the point 0, -6. So this gives us that the derivative is approximately -6 minus 0, that's our change in height, and then 0 minus a -1, that's our change in the x distance. So this gives us a value of -6. This doesn't have any units because there's no context for this problem. Understanding tangent lines and the graphical representation of derivatives also allows us to answer a question like part C. So they want us to determine the correct order for the derivative. So remember, these terms represent numbers. Look at the problem above. F prime of 0 represents -6. So we already have that, and moreover, these numbers are represented graphically as slopes of tangent lines. So all this is asking us to do is compare the slopes of these lines and rank their order from smallest to largest, because the slope of the tangent line is precisely the value of the derivative. So the most negative value is our smallest value, and so that is the slope of this middle tangent line at x equals 0. So that means f prime of 0 is our smallest value. So we don't need to actually estimate these. We can visually just look at the steepness of these lines and very quickly rank the size of these. At x equals 1.1, we see that the slope is also negative, but not as negative. So this is going to be next. And that leaves f prime of -2, which we see as positive, so that must be the largest value. So in the last problem, we saw a few estimates of derivatives using tangent lines. Another thing that we can do with this notion of the tangent line and the correspondence to the derivative is that we can actually plot a derivative of a function given the plot of a curve. So let's go do that now. And probably the best way to do this is to use this connection that when a function is increasing, its instantaneous rate of change at a point or over an interval will be positive. Similarly, so if you can remember this, you can probably remember the other ones. If a function's decreasing, that's equivalent to saying that the rate of change must be negative. And lastly, if a function kind of flattens out, then that's equivalent to saying that the rate of change is 0. So if we wanted to plot the derivative given a function, this gives us a map to move back and forth. So this tells us wherever the function's increasing, the derivative should be positive. Wherever the function is decreasing, the derivative should be negative. And wherever the function flattens out, the derivative should be 0. So I like to start with wherever the function flattens out. So if you look here on the given plot of f at x equals 2 and about 5.5, we see that the function flattens out. And so by flatten out, we mean that if you zoomed in, if you got zoomed in enough, you would kind of be able to stand comfortably on a flat spot. So these will be peaks and valleys, or just places where the function plateaus. So we see at x equals 2 that happens. So I'm just going to draw the tangent line there. And we see that at x equals 5.5. So the slope of these lines are the values of the derivative. So that's precisely what we're noticing. So we can mark this on our derivative plot. This is saying that at these points of 2 and 5.5, the derivative has a height of 0. So we're using this condition here. So those are two easy points in this case to find. And that's just true of any plot that you're working with. The peaks and the valleys, or places where the function plateaus, will always be places where the rate of change is 0, and that's just another way to say the derivative will have a height of 0, or a value of 0. Next, we can notice that our function has been split up into subintervals. So notice from 0 to 2, the function is strictly increasing. And you could draw a tangent line at any point there. So if you just choose this point, let's say about 1/2, then the corresponding tangent line should look something like this. And you can see the slope of that line is positive. So that's just another way to say the derivative is positive at that point. And in fact, any point on this interval from 0 up to 2 will have a positive rate of change, or a positive derivative, a positive slope of tangent. Those are all saying the same things. So that's hitting this first property here. So if the function's increasing, the derivative is positive. So that means we could just take any test point on this interval. So we chose the point 0.5 and just choose some value above the x-axis on the derivative to indicate that the derivative is positive. We're not going to actually calculate and estimate that slope. We're just going to indicate that it is positive. We just want a rough sketch of the derivative. So now we move on to the next subinterval. We could just label these even if we wanted. So subinterval 2, from 2 to 5.5, what's happening to the behavior of the function? So the property that we're looking at is the rate of change. So how is the function increasing or decreasing, or is it neither increasing or decreasing? So we see on this interval the function is decreasing from 2 up to 5.5, and this corresponds to our second property. So we can take a look at that property, and that says that a function is decreasing whenever the derivative is negative, or that's another way to say the rate of change is negative. Choose a point and convince yourself that the slope of the tangent line there will be negative by drawing or sketching a tangent line. The tangent lines are not actually required for this, but I wanted to include many ways to think about this. So at this test point, and in fact any test point we take in this interval, we'll see that the derivative is negative. Lastly, in this third interval from 5.5 to 8, we see the functions increasing, and this is indicative of a positive rate of change, or a positive derivative. Another way to say that is a positive slope of our tangent line. So taking that test point, I just make a little mark there. And by taking these test points in each subinterval, this allows us to have enough information to connect those points and get a rough sketch of the derivative. And so that's all we're trying to do when we're asked this question. So connect those dots, and we have the derivative. So it may be surprising that the derivative itself is also a function, but this is true. So we provided a little bit of a summary. So we discussed what happens that as a function flattens out, so peaks, valleys, plateaus, we always have derivatives that are zero at those points or intervals. And then derivatives are positive wherever the function is increasing. Derivatives are negative wherever the function is decreasing. And that's because when we say derivative, we're saying rate of change. The blue box contains several tips for you to go about sketching these derivatives in a kind of procedural way. So I always recommend finding where the derivatives are zero first. So find where the function flattens out or plateaus. And then look at those subintervals that are created and see in each subinterval is the function increasing or decreasing. This will tell you whether f prime will be positive or negative, respectively. And you can just mark some test points and then connect the dots, and you'll have a nice plot of the derivative. So to summarize in words, the set of relations that we used above, if f prime is positive everywhere, so if the derivative is positive everywhere on an interval, then a function f is said to be increasing over that interval. Similarly, if the derivative is negative over an interval, the function must be decreasing on that interval. And if the derivative is zero on some interval, that's another way to say that the rate of change is zero. So a function then is neither increasing nor decreasing on such an interval. So you can certainly memorize that blue box or kind of internalize that blue box, but I think the easiest thing to remember instead is this information here. This is just the condensed version of that statement. And like I said, if you can remember the first statement, which is that a function is increasing wherever its derivative is positive, then usually you can remember the following two statements as well. So the following problems are practice, so go ahead and pause and try each of these problems, and I'll provide the solutions. So you can see for this problem, the function f never flattens out, so we have no places where the derivative is zero. So if that threw you off, just think back to this problem in the future and remember that even though we're going to check first for places where the derivative is zero, if there are no places where the derivative or rate of change is zero, then we just move on to the next step, which is to look at the remaining intervals and see is the function increasing or decreasing. So you can see that I chose to take 3 different test points just to really confirm my intuition, which is that the function is increasing, so its derivative should be positive everywhere, in fact. And so anywhere we look, we'll see that the tangent line sits right on the line, so the slope of this line is constant. And so I've just made those test points 3, 5, and 7 and indicated a positive derivative value at those test points and then connected the dots. So go ahead and try this one now. So you can see for this function, there is a place where the function flattens out at x equals 3. So we've taken a test point there and sketched the tangent line to remind us that the derivative at that point should be 0. So when we go to plot it on the derivative plot, we should plot a height of 0 at x equals 3. So we did that there, and then we should look at the remaining subintervals. So we see one to the left from 0 to 3, and one to the right of x equals 3 from 3 to 8. From 0 to 3, we see the function is decreasing, so we take a test point anywhere in that interval. Let's choose 1 and sketch the tangent line to confirm that the rate of change is negative there. So we move to our derivative plot and we mark some point below the x-axis to indicate that the derivative function is negative at x equals 1. Lastly, we do the same thing on the remaining subinterval from 3 to 8, and we choose a test point in that interval. I chose x equals 6 and sketched a tangent line. And we see that the function's increasing on that subinterval, and that's just another way to say that the rate of change is positive or that the derivative is positive. So at our test point, we see the slope of our tangent is positive, which agrees with that. And we mark some value above the x-axis on the derivative plot at x equals 6. So you'll follow that same procedure for this last problem, and you should come up with something like this. So there are 2 places where the function flattens out. So there's a peak and a valley, at 1.5 roughly and 4.5 respectively. And so those are places where the derivative will be 0, so we mark a height of 0 on the derivative plot at 1.5 and 4.5. From there, we look at each subinterval and we ask ourselves, is the function increasing or decreasing on that subinterval? And we can verify that by taking a test point and sketching a tangent line and looking at the slope of that tangent line. So this gives us that the derivative is positive in the first subinterval from 0 to 1.5. So using that test point at 1/2, we mark a positive value at that point on the derivative, and then we rinse and repeat with the following subintervals and connect those dots. So we'll let you try the remaining problems on your own, but we'll give you a little bit of guidance with both of these. So for question 4, go ahead and pause and read through that. You can see that we're trying to determine whether these derivatives are positive, negative, or 0, and that's just another way of asking, is the function increasing, decreasing, or neither? So a positive derivative means the function's increasing, and so on. So probably the quickest way to do this would be to plot the function x squared and then look at the corresponding tangent lines, the slopes of those tangent lines at these different values of x. So go ahead and try that and I'll provide the answer. So as we discussed, you should just do a quick plot of this function and then sketch the tangent lines at these values of x, at x equals -1, x equals 0, and x equals 1. And then you can simply look at the slope of those tangent lines, and that will tell you whether the derivative or the rate of change is positive, negative, or 0. The last question uses a table, and it asks us to estimate the instantaneous rate of change. So we may not have seen a problem like this, and so we just need to put together a few different ideas that we've been discussing so far. So the way that we estimate instantaneous rate of change given a table or a plot really is to use a secant line about the point of interest with the smallest interval possible. So since we want to estimate the instantaneous rate of change at 1990, the smallest interval we can choose is 5 years away. So we could choose 1985 to 1990 or 1990 to 1995. So neither one is better because both are estimates that have the smallest interval possible. So choose whichever interval you like the best and then estimate the instantaneous rate of change using that average rate of change calculation. So when you do that over the interval 1990 to 1995, this is what you should come up with, and this represents that the farmland is decreasing by 4.8 million acres per year over that time period.